A very good morning to all the students. I am Dr. Hima Bindu from the Department of Mechanical Engineering. I will be dealing the subject robotics in Institute of Aeronautical Engineering, and my today's topic is definition and terminology from the module 3, that is dynamic motion. So before we start, we need to know what are the various definitions and terminologies which we need to concentrate in module 3. Since it is the dynamic motion concept, so we will be seeing about various different kinematics, or we will be studying about the different Jacobian matrices, or we will be studying about the Roman dynamics, robot dynamics, etc. So firstly, let us see what do we mean by differential kinematics. What is exactly the differential kinematic means? This particular kinematics is relation between the motion, that is the relation between the velocity in the joint space and angular velocity in the task space. That is, it is the relation between velocity in joint space and angular velocity in the task space, right? So the differential kinematics is nothing but the relation between the velocity in the joint space to that of the angular velocity in the task space. That is known as the differential kinematics, which is generally used in the robotics, right? Moving on to the second concept, what is Jacobian matrix? What do we mean by the term Jacobian matrix and why it is being used? Generally, the Jacobian matrix is used to define the joint on the end effector velocity, and it is divided in two terms, right? Generally, Jacobian matrix is used to define the effect of the joints on the end effector velocity. That is each column of the Jacobian matrix, where, for example, when we are writing cos theta or sin theta and 1 or 0, and sin theta, cos theta, 0, 0, 0, 1. When we are generally writing a matrix in this form, each column of the Jacobian matrix defines the effect of the joints on the end effector. Right? Each column defines the effect of the joints. For example, we have taken this as the base, right? This is the end effector, robotic end effector. Now here this is the joint 1 and this is the joint 2. This is link 1, link 2 and link 3. Right? So each column, that is this particular cos theta, is reflected to the angular difference of this joint, right? Angular difference of this particular joint. That's each column of the Jacobian matrix defines the effect of the joint on the end effector, right? This is the end effector, the effect of the joint of the end effector, where the velocity, and it is divided into two terms, right? The first term consists of the effect on the linear velocity v, while the second one depends upon the rotation, right? The first term is considered with the linear and the second term is considered with the rotation, right? The second term we consider with the rotation, right? The first term is considered with the linear velocity, whereas the second term is considered with the rotational velocity, right? So this is about the Jacobian matrix. Jacobian matrix is used to define, each column is defined with the help of the joint on the end effector velocity, and it is divided into two terms, where one term is the linear velocity and the second term is the rotational velocity of the robot, right? Next, what do we mean by robot dynamics? What is robot dynamics? Generally, this particular robot dynamics is used to describe why the things move when force are generated in and applied on the system. When there is some amount of force being applied on the robot joint or robot link, right? So what that is known as the robot joint. What how we do we the robot dynamics provides a description of why things move, right? The manipulator is moving, right, in the forward direction or in the inverse direction, right? Whether it is in the forward direction or whether it is in the inverse direction, in which directions, why the things move when force are generated on an applied system. That is known as the robot dynamics. That is, it describes the movement of the robot. Robots, whether it's a manipulator or the end effector, when we are applying some amount of force, how that why the particular robot things are being moved is being described by the robot dynamics. Right? Next, define principle of virtual work. What do we mean by virtual work? The principle of virtual work is nothing but the principle in mechanics, which is the principle of virtual work, which describes that the fact that configurate constraints actually define forces which do not perform work in the direction of the virtual displacement. That is known as the virtual work. That is, the virtual work is generally used to describe the configuration constraints. Right? The virtual work is used to describe the configuration constraints which define the forces which do not perform work in the direction of the virtual displacement. Next, moving on to the state Lagrangian formulation. What do we mean by Lagrangian formulation? That we need to describe. So here the Lagrangian formulation is used to define the behavior of the work and the energy for the generalized coordinates. Right? It is used to describe the term work and energy. We call it as Q. Right? Here the Lagrangian formulation is used to describe the behavior with respect to the work and the energy for the generalized coordinates. Now this particular approach is the extension of the indirect method. It is an extension of the indirect method where workless forces and the constrained forces are automatically eliminated in this method. Right? Wherever there is no workless forces and constrained forces will be eliminated in the Lagrangian formulation. Right? That is, the Lagrangian formulation is used to describe the behavior of the work and energy for the generalized coordinates in an indirect method. And wherever there is workless forces and constrained forces, that will automatically be eliminated using this particular type of the method. That is known as the Lagrangian formulation. Right? Next, state Newton-Euler's formulation. What do we mean by Newton-Euler's formulation? It is nothing but the combination of the Newton's second law of motion and the Euler's formulation. Right? The combination of Newton second law of motion plus the Euler formulation, right? That is known as the Newton-Euler formulation. That is, it is derived by the direct interpretation of the Newton's second law of motion, which describes the dynamic system in terms of force and momentum. It describes it in terms of force and the momentum. Now, this particular equation is incorporates all the forces and moments acting on the individual robot link. Right? This particular concept involves the force and momentum which are acting on all the individual robot link, including the coupling forces and momentum between the links. Right? The Newton-Euler formulation is derived by the direct interpretation of the Newton's second law of motion, which describes the dynamic system in terms of force and momentum. Right? The equation incorporates all the forces and moment acting on the individual robot link, including the coupling forces between the links. That is known as the Newton-Euler formulation. Next, what is the kinematic tree? What do we mean by kinematic tree? Right? Kinematic tree. What do we mean by the term this? Right, the connectivity of the robot mechanism can be described using the graph in which the nodes represent the bodies, in which the nodes represent the body and the arcs represent the joints, right? And the arcs represent the joints in this kinematic tree, right? In the kinematic tree, it is being described with the help of a graph where the nodes representate the body and the arcs representate the joints. Now, if this particular graph do not contain any cycle, right? If this particular kinematic graph is not containing any form of cycles, then that implies that it is a topological tree. Then the robot mechanism is called as a kinematic tree. In that particular particular robot mechanism, which implies the topological tree, is known as the kinematic tree. That is, if the graph does not contain any form of cycles, then that particular cycle is being considered as a topological tree, and that in the form of robot mechanism is called as a kinematic tree. That is, the connectivity of a robot mechanism can be described using a graph in which the nodes representate the bodies and the arc represents the joints, right? And if this particular graph do not contain any cycle, implying that it is a topological tree, then the robot mechanism is called as a kinematic tree. Right? Next, explain kinematic loop. What do we mean by kinematic loop? Now, if the connectivity graph does not contain cycles, right? If the connectivity graph is not containing any form of cycles, then the robot mechanism contains kinematic loops, and that is called as a closed loop system. Right? And when the robot mechanism contains kinematic loops and that particular is called as a closed loop system. Now, in this particular kinematic loop, we have three dynamic algorithms which we can describe based upon the work which is not being done and the closed loop system. Although they can be used as components in a closed loop dynamic algorithm. Generally, we call the closed loop system have more complicated dynamics and kinematic tree, and they require more sophisticated algorithm to calculate their dynamics. So, right? This particular kinematic loop contains more sophisticated algorithm to calculate this particular dynamics. Right? If the connectivity graph do not contain cycles, then the robot mechanism contains the kinematic loop. That is, if the robot mechanism is has a topological tree, then that particular mechanism is considered as a kinematic loop, and we also call it as the closed loop system. Right? The topological tree is also considered as a kinematic loop, which is called as a closed loop system. Next. What is RNEA? What do we mean by the term RNEA? RNEA means recursive Newton-Euler algorithm. Right? RNEA means recursive Newton-Euler algorithm. This particular algorithm is used to solve the inverse dynamic problem and has a computational complexity on ON. Right? Now, the RNEA means recursive Newton-Euler's algorithm. When this particular algorithm is being given to the robot, then only it can solve the inverse dynamic. That is, when it is moving in the reverse direction, it can solve the inverse dynamic problems. Otherwise, when we are not inserting this particular type of the algorithm, it cannot move in the inverse direction. It cannot solve the problems related to the reverse dynamics. Next, what is ABA? ABA means articulated body algorithm. Now, this particular type of the algorithm is used to solve the forward dynamic problems and has a computational complexity. It is used. Now, RNEA is used to solve inverse dynamics. Right? Whereas ABA, articulated body algorithm, is used to solve forward dynamics. Right? RNA is used to solve the inverse dynamic problems, whereas the articulated body algorithm is used to solve the forward dynamic problems. What is CRBA? CRBA means composite rigid body algorithm, right? CRBA means composite rigid body algorithm. Now, this particular type of the algorithm is used to calculate the joint space, inertial matrix, right? It is used to calculate the joint space matrix and the H matrix, and has a computational complexity of ON2. Here it is ON, here it is O, and it is ON2, ON suffix 2. Right? So here CREA means composite rigid body algorithm. This is generally used to solve the problems on the joint space inertial matrix or the H matrix. Next. Explain workspace control. What do we mean by workspace control? What exactly is the use of the workspace control? That is, a different approach is to transform the dynamics and control the problems in the task space, so that the control law is written in terms of the end effector position or orientation. We refer to this approach as a workspace control. The approach which is written in terms of end effector position and orientation, right? The workspace control which is written in terms of the end effector's position and orientation, that particular approach is known as the workspace control. That is where we have different approaches being taking place between the dynamics and the control problem. And that when it is being termed in terms of end effector position and orientation, that is referred as the workspace control. Clear? So what next? Differentiate fixed and floating bases in robotics. What do we mean by fixed base and what do we mean by floating base in robotics? Fixed base means which is rigid and fixed to the ground level, whereas floating base means if there is no part of the robot mechanism which is fixed, right? That is here. This is the base which is being fixed. And this is the robot which is being moving. This is a fixed base, right? It is a robot which is said to have a fixed base if it is rigidly attached to the fixed support. And an industrial robot arm is a good example of this. This is the industrial robot arm. Right? This is the industrial robot arm, which is a best example of the fixed base. If no part of the robot mechanism is fixed, then it is known as the floating base. If no part of the robot is fixed at one end, then it is called as a floating base. That is, a robot, generally in the industrial applications, we used fixed base type of the robots, where one of the base is being fixed and rigidly attached, and the remaining joints in the links will be in the moving condition. That is known as a fixed base. Where any of the part of the robot mechanism is not fixed, then that particular robot is called as a floating base robot. Next, define motion through a sequence of points. What do we mean motion through a sequence of points? For any given n path points, for example, we have n path points, right? We have n number of path points. For a given n number of path points, when we find the interpolation function through this point n1, order polynomial, then that is known as the motion through a sequence of points. For a given n path points, where we find an interpolation function to these particular points n1 order polynomial, then that is known as the motion through a sequence of a fixed point. Right? Next, define a path. Path means what? When any particular robot have to move from one place to the other, there should be a path being defined. Right, that is the locus of the point in the joint space, which the manipulator has to follow, is the execution of the assigned motion. That is, when the robot has to move from the initial point, initial position, to the final position. Right? when the robot has to move from the initial position to the final position, this particular path has to be fixed, right? This particular path has to be fixed. Then when this path is being fixed, then that is known as the path function. That is the locus of the point where the joint space, which is manipulator has to follow and assign some particular motion, then that is known as the path function. Where when a robot has to move from one initial position to the final initial position, that particular distance when it is traveling, that path has to be fixed and defined so that it will be easy for the robot to have the movement around its particular surrounding. That is known as the path function. So these are the references which we have gone through. So in today's today's session, we have learned about what is meant by a path function, what do we mean by motion through a sequence of points, and what is a space control, or what is the difference between a fixed base robot and a floating base robot, and what are the three types of algorithms which will be used in the robot to calculate the inverse dynamics, forward dynamics, or whether it is a joint space dynamics. What are the three various types of the algorithms, and what do we mean by the kinematic tree, and what do we mean by the kinematic loop, and how it is interlinked with the kinematic tree that we have studied in the kinematic loop system. Right, we have known the difference between the Lagrangian formulation and the difference between the Newton-Euler formulation. That is, Newton-Euler formulation is nothing but the combination of the Newton's second law and the Euler's formulation. We have studied about the principle of virtual work, robot dynamics, and the different kinematics used in the robot, and about the Jacobian matrix. This is all for today's session. Signing off for today, Dr. G. Hima Bindu. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.